they just had a ball. But
It's a miracle we read.
but I was looking at your record. You did it in 4 years with one of them when I was gone. So that's just, I've never heard of it. I didn't even know that happened.
Ready whenever you are, John.
Well, that's what you want, isn't it?
That's what I know, John.
Yeah, you certainly want. I think there's nobody else having coffee yet, so.
Ready whenever you are.
Okay, I'm going to just give it a second here.
Okay.
I think that's it.
You could probably store it.
Okay, we'll just see Ruby up there. No, she's getting coffee. I'll wait 1 second. One more word out. All right, I guess I will kind of encourage getting here on time. It is a great pleasure for, I think, the department, but I think I have to say, especially for me, to introduce today's speaker, Dr. Andrew Winters, Professor Andrew Winters from the University of Colorado, which for some reason they always say CU. They all need to see someone because it's the University of Colorado. So I don't quite understand that. But nonetheless, maybe the only flaw on Andrew's otherwise sterling academic record. Andrew was an undergraduate student here and graduated in 2011, right? Yeah, 2011. And we had an opportunity to work on a project that had occurred, the weather had occurred in May of 2010. We got onto that thing right away, and Andrew just revolutionized the way one looks at these kinds of problems. I mean, I can't emphasize that. I'd never had experience with the Sawyer-Eliason equation solved in an interactive mode. Andrew did that in 2 weeks, one summer after when he started as a master's degree candidate. The list could go on and on and on. What was amazing about this is he graduated as a BS in 2011. I was away for 2014 on my sabbatical, and he graduated with his PhD in 2015. So he did the whole thing in 4 years, and one of those years I wasn't even around. And so pretty unbelievable. After that, he went to SUNY Albany for a postdoc with Dan Kaiser and Lance Bosat. Then he had 2 more years at SUNY Albany that he earned through an NSF postdoctoral fellowship. So he spent 4 years at Albany working with some of the best people in the world on these problems. And actually what he was doing was he's biding his time. He had several different offers that he could have taken, and he made some tough decisions to turn them down because he knows his value. And that's something everybody should think about all the time, even especially students, but especially the students. Don't jump at the first offer. If you're good, someone else will come along. And sure enough, Colorado came along. And Andrew's been there since 2019. And about a month into his tenure at Colorado, we were together in Munich at an old German monastery in the Catholic part of Bavaria, right? And we're watching the wild card game. Andrew's from Milwaukee, so he's a big Bucks fan and a diehard Brewers fan, and he's a great golfer. Although his drive, it's so perfect. If he just put a little more energy into it, he'd beat me in the drive. He doesn't yet, but it's always more accurate. We're watching the wild card game in 2019 at 3 to 5 a.m. in the morning in Munich in an old Trappist monastery, and it was going well for us till the 8th inning, and we lost the game in the 9th. And we both, I think, I can speak for myself, I wanted to curse to high heaven, but you couldn't say a word in this place at that hour, and it was very frustrating. But there's no one else on earth I would rather have had that experience, frustrating though it was, than Andrew Winters. So I'm really happy to have Andrew here today. He's going to tell us today about regime-dependent predictability of cold season precipitation events in the St. Lawrence River Valley. Andrew, welcome.
Yeah. Thanks, John, for that great introduction, and thanks to Steph, too, for the invitation. And yeah, there was a pretty somber breakfast after that game came to an end. I don't think I remember much from the presentations later on, either from just the lack of sleep.
I had to give Michael's presentation on adjoints 2 hours after the
See, that's probably one of the most impressive achievements overall. But yeah, super honored to be here, especially after sort of so much time spent at UW. This place holds a pretty special place in my heart for many different reasons. The department here being one of those first and foremost. And I'm excited to talk to all of you today about a project that I was involved in a couple of years ago in the St. Lawrence River Valley up near Montreal, where we were focused on trying to understand the synoptic dynamics associated with mixed precipitation events in areas of complex terrain. And so we'll dig into that a little bit more in detail here, but I just want to thank a few of my collaborators on this particular work, which I'm showing here, including Nick Basel, who is also a UW alum, and John Jacob, Justin Minder, and Clary Ryer, who's in our group at CU. So just to get things started here, this project, which we refer to as WINTRE-MIX, stands for the Winter Precipitation Type Research Multi-Scale Experiment. I know it doesn't fit the acronym, but we did our best to come up with something that I think has a really good ring to it. The whole goal of this campaign is to better understand the multi-scale processes that are influencing precipitation type and amount within areas of complex terrain. And to first order, this whole process is really governed by both the magnitude and the intensity of an elevated warm layer either above the surface or one that connects down towards the surface, because that dictates how precipitation particles are changing their habit as they move towards the surface of the Earth. And so understanding how this particular process is predicted and represented within models is pretty paramount towards understanding where are going to be those locations that are most susceptible to, say, freezing rain versus all rain or snow in a given location. And so we had three primary goals of this particular campaign. We had some objectives that are focused on understanding the evolution of microphysics, the sort of relationship also of these events to the land surface characteristics and to microscale turbulence. We have some focus on mesoscale dynamics as well, including understanding the role of frontogenesis zones and their interaction with the complex terrain and the resultant sort of formulation in the form of snowbands. And then for our group, we're really focused more on the synoptic dynamics of these events, so trying to better understand sort of the large-scale environments that produce these types of events across the St. Lawrence River Valley. How well are these predicted, say, on 0 to 5 day timescales? And so for the majority of this talk, we'll focus on sort of the synoptic dynamics piece. So why the St. Lawrence River Valley? Well, this area, as shown by this particular graph to the right, is characterized by one of the greatest frequencies of freezing rain occurrence across the northeastern U.S. or across North America in general. Part of that is due to the presence of relatively favorable terrain, which I'll highlight here in a second, but essentially the St. Lawrence River Valley right here is right near sea level, and it's flanked by different areas of topography to the south, say the Adirondack Mountains to the south. You've got the Green Mountains into Vermont to the east, and then the Laurentians to the northwest, all of which rise several thousand feet above mean sea level. So you have a pretty substantial orographic contrast in that region, which sets up a pretty favorable environment for cold air to pool right near sea level in the vicinity of, say, the Montreal area. And that cool air can be particularly conducive to higher frequencies of freezing rain events. And just to highlight one of the more notable events within the literature, the January 1998 ice storm is one of the biggest ice storms to impact this particular region, resulting in multiple inches of ice accumulation within the blue shaded areas there. And then you can see a couple of pictures from the National Weather Service there that just highlights the sheer extent of ice accumulation through one of these more impactful events. This isn't just impactful to, let's say, property, but there's big considerations also for infrastructure, commerce, and transportation is particularly difficult. So for our particular field campaign, it was conducted over a 6-week period from the 1st of February through March, mid-March of 2022, right during the middle of sort of an uptick in coronavirus cases, which introduced its own particular challenges. We had a Dow radar that had trouble getting across the border because one of the drivers of that vehicle came down with COVID right before they were supposed to cross the border. We had pretty strict isolation criteria for all of our different team members, which included groups at the University of Quebec at Montreal, McGill University, University at Albany, University of Colorado, and also University of Wyoming. We all had to basically sequester with our respective university groups for the duration of the campaign to ensure the continuity of operations. We got a pretty blessed period as far as weather went across the region. We had 11 different IOPs that we were able to sample. A couple of them were pretty impactful freezing rain events, particularly during the middle of the campaign. And just to highlight some of the assets we had in place, on the left-hand side is a map of the topography and the shading, which really highlights sort of the unique area that the St. Lawrence River Valley is, all the way down to sea level compared to these flanking areas of orography, but also some of the existing permanent surface observation stations and operational radars here in the Pentagons. But on the right-hand side is everything that we instituted as part of the campaign itself, including a number of different surface radiosonde stations that were launched all up and down the Champlain in St. Lawrence River Valley during these particular IOPs. We had an airplane that would either target a St. Lawrence, Champlain, or Champlain Valley domain, depending on where the forecast was setting up. We also had a number of augmented surface station sites that had additional observations, including radiometer data and LiDAR data. And that helped to give us sort of an ability to really transform our observations of these storms and greater temporal capabilities than we ever were in the past. And if you want to learn more about the campaign in general, all of the different objectives, we've got an article out in BAMS that you could take a look at. And before we get into research, just some of the fun photos from this particular event. These are a couple of sites where we had the Dow radar stationed across portions of northern New York and southern Quebec. This was pretty difficult on some days where we had sort of rain on snow type events. Basically, we were parking these Dow radars in the middle of farmers' fields, so as that snow melted, it created pretty muddy and sort of soggy conditions. In one situation, we actually had to abandon the radar because the water levels were starting to rise too high around the Dow, and we would end up with situations where we'd end up with pretty wet feet by the end of the IOP if we didn't get out of there quickly. But we had sort of our airplane, which was provided by the National Research Council of Canada, which largely took those microphysical observations. And then we had our surface sounding teams, which arguably had the toughest job of anybody being stuck out in 34, 33 degrees and sort of moderate rain most of the time, dealing with trying to launch these weather balloons in a coordinated way across the domain. But we got some great sort of observations there. But in terms of the focus of this particular talk, especially with more of, let's say, a synoptic tenor to it, one of the things that showed up during the campaign was we had a variety of different weather systems impact the domain and deliver mixed precipitation. We had clipper systems, which largely characterized the early part of our field campaign. These particular low tracks here highlight the tracks of two separate IOPs from early February that took on more of an Alberta clipper type track across the region and brought more meager precipitation amounts. We had more notable events, such as a nor'easter or east coast cyclone. This was IOP 6 that brought purely snow to our particular domain, but followed a pretty classic Miller B type scenario where it redeveloped to the east of the Appalachians and moved just south of New York City. This particular event was one where we had the opportunity to perform synergistic observations with the impacts field campaign that was based more across the East Coast, so we were able to team up our resources for that event. And then some more of the impactful events that brought the largest amounts of freezing rain were these Colorado low type tracks that moved from, say, the Texas Panhandle up through northern New York and IOP4. This was an event that largely brought sort of substantial amounts of rain and then freezing rain across the region and sort of more of a rain to snow transition. And then IOP5 here, which featured a low that took a more northern track and featured a transition, say, from more snow to rain across the region and pretty substantial freezing rain totals overall with some of the warm advection we had out in front of this surface cyclone. And just to highlight one of the soundings we took during this fifth IOP to kind of just give a sense of the type of the cold air depth that we were dealing with some of these freezing rain events. My cursor here is highlighting the 0 degree Celsius isotherm on this SKU-T diagram, which shows this pretty deep and extensive warm nose right above the surface, but also this drop of almost 10 degrees Celsius within the lowest few hundred meters near the Earth's surface. You can almost reach up and touch the warm layer from the surface, just for how thin this cold air layer was. But it gives you a sense of just how difficult modeling these types of events are in terms of how fine some of these cold and warm air layers are in these particular events. And to give you another sense of just how sort of challenging this event is for models, perhaps at longer forecast lead times. Shown here to the right in all the color contours are forecasts at 48 hours of the position of the 0 degrees Celsius isotherm at the surface at the start of that fourth IOP. The black line here is essentially the verification at the same time. And you can see not only just the tremendous spread in the ensemble at this 2-day lead time, but how the model ensemble itself was pretty sort of off compared to the actual observations at this particular time. And we're dealing with a situation where just small shifts in the position of that 0 degrees Celsius isotherm have big implications for just a cold, wet rain versus accreting freezing rain that can make travel pretty impassable. And so for this particular project, our goals are really to understand, based off of the different, let's say, cyclone track types that impact the region, can we cluster these surface cyclones and examine their characteristics as a function of track in terms of what type of precipitation type are they most associated with? And then how can we gauge whether these sort of cyclone characteristics are predicted at synoptic timescales, say at 0 to 5 day forecast lead times? So for the remainder of the talk, we'll focus on first sort of this methodology for identifying cyclone clusters and a way in which we can characterize the thermodynamic environment that surrounds the passage of these different surface cyclones. We'll then look at the climatological characteristics of these different cyclone tracks we'll come up with, and then we'll dig a little bit more into the predictability of their characteristics to finish things out. So to start things off, as far as our methods, the first thing we need to do is come up with these different cyclone clusters. And what we did was take a surface cyclone data set from Mikkel Sprenger et al., which is applied to ERA interim data between October and April of 2000 to 2018. And we took those cyclones and isolated those that form basically to the east of the continental divide within this green sort of trapezoid here. And we wanted to examine those cyclones that pass through this box centered on the St. Lawrence River Valley, with the motivation that cyclones passing through that domain were likely to impact the sensible weather across the St. Lawrence River Valley most prominently. Once we identified those cyclones, we also then required them to be associated with observed precipitation at both Montreal and Burlington in their long-term observational sites. This was to verify that we didn't just have cyclones that led to the lack of any precipitation, but we're actually translating to some observable precipitation during that time period in which the cyclones passed through that box centered on the St. Lawrence River Valley. And then after that, we clustered the genesis points of these cyclones, which is indicated by the colored dots here. So each one of these dots is a genesis point of one of those cyclones that's met our criteria, and then they're colored according to the results of that k-means clustering algorithm, which we tested with a number of different clusters and metrics to make sure we ended up with the most physical distribution of cyclones and their accompanying tracks that made sort of synoptic sense under this particular situation. And based off of these different groups here, which include a West Canada track, an East Canada track, a Central US cyclone track, and then an East Coast track, all of these individual cyclones group well into some of these sort of canonical synoptic evolutions that we would expect to impact this particular location. So shown in each diagram, the colored lines here represent the cyclone tracks of each constituent cyclone within that cluster. The white dot here is just to help orient you to the center of that St. Lawrence River Valley domain. And then the thicker colored contour here on this particular map basically is a normalized track for each of these cyclone types, which is normalized basically by the duration of each cyclone. So in a sense, each one of these segments represents a progression from 0 to 5% to 10% into the life cycle of that cyclone before it reaches its lysis within that Sprenger et al. Data set. And the intensity of these cyclones on average during this sort of normalized evolution is colored according to the color bar down here. So it basically gives you a sense of when in the life cycle of these storms are they typically impacting the St. Lawrence River Valley? Are they occurring right near the time in which these cyclones are undergoing genesis? Or in the case of these West Canadian Clipper type systems, are they impacting the St. Lawrence River Valley near the end of their life cycle or when they're in their most mature stage? And so we can see some sort of different characteristics there. The Eastern Canada cluster is a little bit earlier on in the life cycle, where the central U.S. cyclone tends to impact these St. Lawrence River Valley right near sort of its peak intensity moving across the region. So once we've identified these different cyclone tracks, the next step was to isolate profiles of the vertical temperature anomalies over the St. Lawrence River Valley. And for this, we used the ERA5 data during a 48-hour period centered on the time of each cyclone's closest track to the center of that St. Lawrence River Valley domain. So in a sense, what we want to do is isolate the character of the temperature anomaly profile during that 48-hour period in which the cyclone is impacting the region. We use the temperature anomaly profiles here to sort of remove the impacts of the seasonal cycle on the temperature the temperature structure as these cyclones move through the region. Otherwise, for this next step here, we'd basically be isolating how the temperature profiles are going to be sorting as a function of time of year and not necessarily based on the synoptic character of the flow that accompanies these various cyclones. And we parsed out the different temperature anomaly profiles using a self-organizing map. And so what's shown here is a result of that self-organizing map. If you're unfamiliar with sort of this machine learning technique, it's an unsupervised learning technique that groups similar data records together into two-dimensional arrays of a user-defined number of nodes. And so we tested out a variety of different settings for this particular SOM, and ultimately found the one shown here to be the most representative of those vertical temperature anomaly profiles during the 48-hour period encompassing that SOM. And if you have any or accompanying that cyclone. And if you have any questions on some more of the nitty-gritty details on how we sort of settled on the SOM, I'm happy to take those questions afterwards. But ultimately, what you can see from these sort of different temperature anomaly structures is a variety of different features in terms of how those anomalies look during the time period in which those cyclones are impacting the region. So if you look on the far right-hand side of the SOM, notice we have profiles here with largely above normal temperatures within deep layers, either immediately above the surface or throughout the entire depth of the tropopause, or the troposphere. Whereas on the left-hand side, we have approximately the opposite, where temperatures are generally below normal through a considerable depth of the troposphere. If you look at some of the near-surface characteristics across the top row, notice we have sort of generally profiles near the surface that feature below normal temperatures across all four of those nodes along the top, whereas on the bottom, we generally see surface temperature anomalies that are somewhat above normal overall. So the main thing I think to take away here is we're seeing the SOM sort of pick out on variations in the temperature anomaly profile, both within sort of the lower to middle troposphere, which is somewhat important for capturing sort of the position of where that warm nose is in the vicinity of these events, but also the character of the near surface temperature anomalies as well, which is important for characterizing the environment into which this precipitation is falling into. Temperature anomalies, while they're helpful in sort of normalizing for the character of that synoptic environment, and by removing the seasonal cycle, it can be sort of useful in that perspective. It's not maybe synoptically intuitive. So shown here is a composite of what those temperature profiles look like within the SOM if you take every day that assigns to each node and composite the actual observed temperatures associated with that particular temperature profile for each node. What you'll notice again are some profiles here on the right-hand side that suggest a profile that's somewhat isothermal here in the composite, which may be favorable for some more of those mixed precipitation types. Whereas on the far left-hand side, you see generally temperature profiles that are below 0 degrees Celsius over a considerable depth of the troposphere, really supportive of, let's say, snow under those particular circumstances. So these two sort of frameworks are going to comprise how we're going to analyze this data moving forward. We're going to have those cyclone clusters that will sort of guide us with that partition of the different synoptic events that are going to impact the region. And then we'll have this SOM here to investigate how the temperature profile varies within these particular events. So with that in mind, let's look at some of the climatological characteristics of these events before we dig into their predictability a little bit more. What you can see from this particular histogram during the cold season is that in general, the East Coast cyclones are going to be most frequent during December through March overall compared to all other months during the cold season. The central U.S. cyclones, the ones that track, say, from Colorado across the Great Lakes, are somewhat less frequent in October and November, but become more frequent as you move later on in the cool season. And then the Clipper-type systems are generally more common during the first half of the cool season and become less common comparatively as you move past February into April. Looking at the characteristic cyclone intensities as a function of month, here are some box and whisker plots that extend from the 5th percentile up to the 95th percentile. The colored boxes represent the interquartile range, and the dashed black line there represents the median for each cluster in a given month. Overall, the main thing to take away is that the East Coast and central U.S. cyclones feature lower minimum sea level pressures during the heart of the cool season. You can see how the blue and orange bars here are generally lower during the heart of the cool season compared to those two Clipper-type clusters. The gray bar here is just the sum of all cyclones, so it gives you a sense or a basis of comparison if you consider the full subset rather than that partition set of cyclones. But outside of, let's say, the heart of the cool season, there's generally no major differences in sort of the maximum or the minimum central pressure of these cyclones, say in October and November, or into, say, sort of March and April in general. In terms of the type of precipitation that accompanies these different cyclones, shown here is a pretty complicated plot that I'll introduce sort of in stages here. The black dashed contours are the composite mean sea level pressure anomalies associated with each cyclone type. The dot here represents the sort of average location of each cyclone type at its closest passage to the center of that St. Lawrence River Valley domain. And then the shading here, if you ignore sort of the hatching and the stippling for a second, just tells you whether a location or the probability of precipitation at a given location during that particular event type. So for example, if we look at, say, the East Coast cyclones, we have a much greater probability of rain, say, over the Gulf Stream here during these particular events, say, than we do rain across the St. Lawrence River Valley sort of during these West and East Canada systems. Generally a greater probability of rain southeast of the cyclone during central U.S. events as well. But the main takeaway for the St. Lawrence River Valley is that if you want rain probabilities to be maximized in the St. Lawrence River Valley for one of these different cyclone types, it's generally the central U.S. one that you want, where you have sort of these highest probabilities right near Montreal and generally less probabilities of rain for these other various systems. If you look at the hatching here and the stippling, that is sort of evaluating significance of a probability of precipitation relative to the location of the cyclone center. So not in a spatial absolute framework like we have here plotted in the shading, but more so if you have, let's say, a hatching here, it means that relative or at that particular radius, relative to the cyclone center, the probabilities of rain are greater than what you'd expect than compared to the full sample of cyclones that are impacting the region. So it's generally a greater elevated likelihood of rain at all, let's say, radii relative to the surface cyclone, where you see that hatching there. The stippling represents a reduced likelihood of that precipitation type at those radii relative to the cyclone center. So in general, it should make sense for your more colder Clipper systems that there's generally a lower likelihood of rain in all sort of radii relative to the surface cyclone for those systems across these various areas of the St. Lawrence River Valley. Whereas for some of these warmer type systems, you generally have greater probabilities of rain that are moving across the region. If we look at the snow probabilities across the St. Lawrence River Valley, you generally see the brightest blues for your sort of nor'easter type scenario across the St. Lawrence River Valley, or for your Clipper type systems, where you generally see those higher probabilities of snow. But overall, you see greater probabilities of snow at all radii relative to the cyclone center during your clipper systems compared to what you see for the East Coast and central US storms. In terms of sort of the more, let's say, interesting or hazardous types that we might consider as part of WINTRE-MIX, it's really the central US cluster that's the biggest winner for the greatest probabilities of freezing rain right along the warm frontal boundary. Same thing with ice pellets too. But notice that those probabilities are considerably less or are much rarer in the data set compared to instances of rain or snow, which might make sense there. We can also use the SOM we developed to look at the relative frequency of each temperature anomaly node during each one of these cyclone events. And so the height of these individual colored bars represent the number of hours associated with each group, or the percent of the hours in each node that are associated with each group. So for example, in node 12, the largest fraction of times in that node are associated with the central US sort of cyclones, which are generally tracking over the Great Lakes region and generally to the west of the St. Lawrence River Valley. If you look at the dark shading beneath here, where you've got this sort of gray fill, this is when you look at the total number of hours spent in that node regardless of the cyclone type. So one thing to point out when you look across the far right-hand side of the SOM is notice the total number of node hours generally peaks for these nodes on the far right-hand side during the early hours prior to that cyclone's closest passage to the St. Lawrence River Valley, which makes sense because before that cyclone moves through, you should expect some advection of warm air into the region, and those warmer lower tropospheric temperature profiles should prevail. But if you look on the far left-hand side of the SOM, notice these colder lower tropospheric nodes generally peak after the time of the cyclone's passage, which coincides with that cold air advection as the cyclone departs to the north and east from that particular region. If you compare the different cyclone types, generally we see these nodes on the far right-hand side are dominated the most by this central US cluster, where you're able to get that stronger warm air advection into the region. The East Coast cyclones really dominate the colder nodes here, where you're generally locked into cold air on the northwest side of the cyclone as it passes over the Gulf Stream. And then interestingly, both of the clipper nodes here generally spend roughly about the same amount of time in each node overall. They don't tend to have any sort of preferred node compared to that central US or that East Coast cluster. So let's sort of finish off the talk by considering some of the predictability of the characteristics associated with each of these sort of cyclone evolutions. And for this, we use the GEFS version 12 reforecast data set, which has 5 different ensemble members that are initialized at 0 UTC every day going back to 2000. So we can end up with sort of a full, almost 19-year sort of period in which we've got these sort of cyclones and their sort of forecasted characteristics at synoptic timescales across a number of different ensemble members. We'll use these GEFS reforecasts to characterize errors in the cyclone position and minimum central pressure at the time of each cyclone's closest passage to that St. Lawrence River Valley. And we'll also look at errors in the vertical temperature profile during those sort of 48-hour periods centered on the time of each cyclone's closest passage to the St. Lawrence River Valley. So in terms of some basic characteristics to start, shown here on the left-hand side is the number of valid forecasts of each cyclone type as a function of forecast lead time. You may notice this sort of soft-tooth pattern here and find that particularly spurious. The reason why that's the case is this is only a function of basically the number of events that are sorted into each 6-hour synoptic time step. And since we only have forecasts that are initialized at 0 UTC, you basically only get sort of one forecast at 24-hour intervals of that particular event moving forward in time. So that's just sort of a representation in a way of the number of events that self-sort themselves at each synoptic time. And then the dashed lines here on the bottom, this is sort of a representation of forecasts for each event type that do not have any representation of a surface cyclone within some radius that varies as a function of forecast lead time relative to the observed cyclone. One thing that you might notice here is that there's generally larger numbers of missed forecasts for the East Coast and the Eastern Canada cyclone cluster. Part of this we hypothesize is due to the fact that these types of cyclones are undergoing genesis right near the St. Lawrence River Valley. So the lack of forecast there might be a result of the fact that in the forecast, the cyclones have not formed sort of a minimum central pressure yet. It's more of, let's say, sort of an amorphous area of lower pressure that we can't pick up on. And you see fewer missed forecasts for the West Canada and central US clusters because those cyclones are passing through the domain much longer into their life cycle and are thus much more likely to be well formed. When we look at the average track error, average absolute distance error in those forecast tracks, we really don't see any differences between the different clusters here, just a general increase in the distance error or the average distance error as a function of time. We also notice no substantial differences in the minimum central pressure of those cyclones as a function of time between the different groups, but generally just a fact, sort of an observation that the cyclones within the GEFs tend to feature lower pressures than what we see within the reanalysis data set, which may just be a function of the differing resolutions and characters of those data sets. But notice that that error is not also changing in time either. So that's also a function that it might be just more of an intermodal difference there rather than something inherently physical. But where we get to see more interesting results are from these particular diagrams here, which are looking at the forecast track error as a function of forecast lead time. So as the dots get larger, you increase in forecast lead time by 24 hours, where those largest dots represent errors 5 days before those cyclones make their closest passage to the St. Lawrence River Valley. And then we express these errors in a track relative framework. So for each cyclone, we define the cyclone to be moving in the direction of this black arrow. We can then look at those tracks in the forecast as being left of that sort of motion of the cyclone, right of that motion, or too slow or fast relative to the observed cyclone. Across all of these different groups, we see a common result that the forecasted cyclones are generally too slow and left of track relative to verification, which has implications for how temperatures are likely changing across the region during these particular events. If you're delaying, let's say, the onset of that warm or cold air advection across the region. But just to give you a sense that what we were looking at before was just a large average of these different events, there's still considerable spread in the track errors as represented by these frequency distributions here for the different event types. So this just shows where you see track errors most frequently within this sort of phase diagram type perspective. You see there's events that are sort of too fast, left of track, right of track. They fit all modes there. So not every cyclone we see is too slow and left of track, which certainly complicates the analysis. But what we see that's somewhat interesting when we partition events by the quadrant of these phase diagrams is we see that uniformly, cyclones that generally track left of track tend to be too strong relative to those that track right of track, which feature sort of pressure errors that are either, let's say, greater than the observed cyclone or not as sort of, let's say, weak or as strong as, let's say, we see for those that are left of track, which may have also some implications there. So what we hypothesize is that if the cyclones are stronger, they're likely driving stronger warm air advection out in front of them due to that minimum central pressure. That drives the baroclinicity farther poleward, and if that cyclone is roughly tracking in the direction of the thermal wind, its track is going to be roughly sort of farther poleward, let's say, in that hypothetical example compared to what we see in the observation. So that's one of the sort of core ideas we have for potentially explaining that particular evolution. It may also be the fact that these cyclones within the models are going through their life cycle too fast, so they're reaching maturity faster than they are in reality, which also has implications in terms of how that baroclinicity is rearranged. In terms of the predictability of temperatures here, things get a little bit more complicated to analyze a bit due to some of the differences we see between reanalysis products. So ultimately shown here on the left is the sort of GEFS forecast temperature bias relative to the ERA5. So we take the GEFS temperatures and subtract them from the ERA5. And this is shown as a function of forecast lead time, where the contours get darker as we move towards larger forecast lead times. If you just looked at this comparison with respect to ERA5, you notice that the GEFS exhibits this really sort of strong cold bias near the surface, is pretty good in the middle troposphere, but then is biased cold once you get into the upper troposphere and lower stratosphere. But part of this should be taken with a grain of salt, because shown here to the right is the difference at each, let's say, hour relative to the time of each cyclone's closest passage of temperatures between the ERA5 and the CFSR. And notice that at all times here, during that 48-hour period in which the cyclone is making its closest passage, there's a relatively similar shape to the temperature contours here, which suggests that some of the interim sort of reanalysis differences are consistent across the entire life cycle of the cyclone as it's moving through the region. But you'll notice that the ERA5 compared to the CFSR is generally too warm at low levels and too cold, let's say, within the middle and lower troposphere, which really complicates our analyses of these temperature predictions, primarily from the standpoint because we can't necessarily determine whether these differences are sort of truly due to something physical or just due to intermodal differences as a whole. So that's sort of something that complicates things a bit. Because of these differences between the reanalysis products, for the remainder of this talk, I'm only going to consider the forecast temperature biases relative to the 6-hour GEFS forecast error here. Because ideally, you would presume that your 6-hour forecast of synoptic conditions should be performing the best, because it's going to have the shortest lead time prior to verification. And so if we look at subsequent lead times relative to that, we get sort of a better sense of how the model is biased at subsequent forecast lead times, with the underlying assumption that that 6-hour forecast is still going to be containing its own biases relative to reanalysis. But at least in this way, we can see how those biases are evolving in the model world as a whole. So what we see here relative to the 6-hour GEFS forecast is that as you increase forecast lead time, the cold bias near the surface gets stronger, and the same thing happens within the upper troposphere as a whole. At shorter lead times, it's actually biased a little bit too warm within the middle troposphere at those short forecast lead times. So with that in mind, we can then look at differences across the different cyclone event types, which offer some pretty interesting results here. We see for the East Coast cyclones, it's generally biased to be a bit too warm within the lower troposphere. For the central US events, we see that it starts at short forecast lead times, being biased warm in the lower troposphere, but progresses towards a cold bias towards longer lead times. And then for the Clipper type systems, we see a bias towards colder temperatures much more substantially, even at short forecast lead times within the lower troposphere. Some of these differences can be summarized a little bit more clearly if we just look at sort of a superposition of all the different sort of event types at a common forecast lead time. So what's shown here is the forecast temperature error at 120 hours prior to that cyclone's closest passage to the St. Lawrence River Valley. And this sort of difference, or this sort of temperature bias here, is expressed relative to the average error of all 5-day forecasts. So in a sense, it's looking at how the 5-day forecast error varies as a function of event type relative to that average 5-day forecast error. And from here, it's really easy to see this warm bias for the East Coast cyclones that reaches almost 0.3 to 0.4 degrees Celsius when you're dealing with, let's say, these events when you're right on the edge of rain, sleet, freezing rain, may seem initially small, but has a huge impact when you're talking about that sort of transition between these different event types. You also see that sort of cold bias within the central US events, especially within the middle troposphere. Anywhere where you see these dots are where you have statistically significant differences relative to that full collection of cold season precipitation events that we're looking at. And then for the Clipper systems, you really see that near surface cold bias show up substantially there. So some pretty interesting differences there as a function of event type. We also see really interesting differences when you partition the profiles based off the observed precipitation at Burlington, Vermont, and Montreal. So what we've done is self-sort all of the temperature anomaly profiles based off of the prevailing weather reported at those observation stations. This gold line here represents the presence of any active weather: rain, snow, freezing rain, sleet. The purple line is the lack of any weather. There's definitely going to be time periods in that 48-hour period centered on the cyclone's passage where there is no precipitation occurring. And then the last three colors here represent the different precipitation types all on their own. What's interesting, if you look at, let's say, the freezing rain events, it's biased slightly too warm near the surface by maybe a quarter degree, but you have a substantial cold bias within your warm nose that's almost -2 to 2.5 degrees Celsius compared to observations right within that layer where it's really important to gauge the magnitude of that sort of warm air through which those precipitation particles are falling through. You also see cold biases for your rain and for the full active weather sort of category here within sort of the middle and lower troposphere there. Part of the reason why we're seeing potentially these cold biases here is hypothesized to be a result of perhaps how the microphysics schemes in the model are handling the phase changes of the precipitation particles. If they're falling through that layer and melting, giving off latent heat in that particular scenario, or absorbing latent heat, I should say, in that scenario to melt in that subsequent position, that if you're not getting that absorption of heat correctly or overdoing it, you're going to end up with some of these temperature biases. And similarly, near the surface, this warm bias here may be also a result of how that sort of phase change is being dealt with when those precipitation particles make contact with the ground, refreeze, and give off latent heat in that particular scenario. Notice you have a warm bias for snow. Those precipitation particles are not undergoing phase changes as they fall down towards the surface of the Earth. So you might be seeing some of the differences there that sort of are a reason why we see that distinction. All right, so just to kind of finish things up here, this is sort of an expression of these forecast temperature errors as a function of node, expressed relative to the average 6-hour forecast error for each of these nodes themselves. The main takeaways that I want you to walk away from is if you look, let's say, at node 12 here, which is largely a node that prevails prior to a cyclone's passage across the region, you're generally biased to cold, and that cold bias gets stronger as you move further away from an event. Whereas if you look at, let's say, node 1, which represents what your most typical node is prior to the, or I should say after the cyclone's passage, you generally have this warm bias in the middle and lower troposphere, traditionally when you'd expect that cold air regime to emerge. So some of these key observations that we'll put together here in a second is that we found that these forecast cyclones are generally left of track, too slow and too strong relative to what we see in the reanalysis. We find that forecasted temperatures are generally forecasted to be too cold prior to a cyclone's movement across the St. Lawrence River Valley, and then afterwards it's too warm. And then we also find that near-surface temperatures are biased to be too cold for West Canada and East Canada events, and for Central US events too, and are biased warm for those East Coast events. How can we sort of synthesize this into what sort of, in terms of how the models are depicting these situations? So what I'm showing here is a spatial map of the sort of 850 hectopascal temperature errors in the shading for each different cyclone type here on the left. The middle column is showing the 850 hectopascal meridional wind error in the shading. And then we have near surface variables on the right-hand side for 2-meter temperature and for 10-meter winds overall. The main thing to take away here is if we're looking at, let's say, the winds both at 850 and 850 hectopascals and 10 meters, is that within sort of this amalgamation of forecasts, the meridional wind is not southerly enough out in front of the cyclone here. which at first may seem counterintuitive because you said we found these surface cyclones to feature lower minimum pressures than what we're seeing in the reanalysis, wouldn't you expect stronger warm air advection? That's definitely true, but I think what we're seeing here is more of a function of the slow bias within the model itself. If that cyclone is not propagating into the region fast enough, you're not able to get into the strongest warm air advection, and it shows up as a negative southerly wind bias in each of these cases. If you're not getting that strong warm air advection, you're not getting warm enough temperatures out in front of that cyclone. So that's what we think is happening or manifest within these particular plots. We're trying to do the same thing from a cyclone relative framework, so taking the positions of the forecasting cyclones, layering them on top of one another to see if there's any inherent differences in the representation of each cyclone as a whole. But at least from this spatial perspective, ultimately I think what we're seeing is sort of a reflection of that slow bias and its influence on temperatures both for 850 and 2 meters. The other thing I want to resolve here is this fact that, let's say we have, sort of with the East Coast cyclones, we saw that generally temperatures were biased to be too warm during those events. I think the same mechanism is at play here, because generally if this cyclone is tracking to the south of this region, let's say at this time 0, you're delaying the onset of the cold air advection. So as a result, your temperature bias is a function of that cold air advection not kicking in fast enough. Whereas with the other cyclone types, where you're getting out in front of that cyclone arriving through the region, you're just not kicking in the warm air advection fast enough. And that's translating to some of those differences we're seeing. So just to summarize, we found that the precipitation type across the St. Lawrence River Valley is really strongly dependent on cyclone track, and some really interesting results on how precipitation types are preferred relative to the cyclone center overall. And we found that central U.S. cyclone track really was the one that gave us the greater likelihoods of freezing rain and ice pellets. We saw from the forecast that cyclones are generally too slow left of track and too strong at 0 to 5 day forecast lead times. This too slow bias is really what's responsible for some of these lower tropospheric and near surface temperature biases that we saw as a function of cyclone track. And we also saw during periods of different types of precipitation, there were interesting biases in the temperature that might sort of be due to some of the microphysical or the handling of the microphysical properties of those precipitation particles as they move through that warm layer and undergo phase changes. So with that, I'd like to thank you all for your time. Thanks again for the invitation. It's really been humbling to be back here, and I'll use any remaining time to take any questions.
We have a tradition now that you might be unfamiliar with, where we let students ask the first question, which is a great idea. Grant.
Could you go back to the frequency quadrant map?
Yeah, for the precip types?
For the too slow and left to track.
Oh, yeah.
It seems like they all, except for the West Canada, have a bit of a node where it's the right speed and 1,000 kilometers to 1,200 kilometers too far to the left. I'm not too familiar with the region, but is there any sort of geographical steering going on there?
Yeah, that's a great question. So like for this East Coast cyclone, you've got sort of this node up here. My thought about these is you're likely seeing some potential situation where maybe those cyclones are passing, let's say, over the Appalachians, and you're not necessarily getting the handoff of the cyclone and its redevelopment to the lee of the Appalachians. Because that both of these sort of cyclones, both for central U.S. and East Coast, are likely to be sort of dealing with some type of those terrain interactions. But it'd be interesting to look at those in a bit more detail, but that's my thinking.
Yeah, thank you.
Rudra.
Hey Andrew, great talk. I had a quick question about the seasonality of storms you mentioned earlier, and I was wondering whether these biases change based on the early winter or the late winter season, or they remain constant and seasonality is not a factor.
That's a really good question. We didn't look specifically into sort of how those characteristics change as a function of the time in the cool season. I think especially for the precip type, that might be really interesting, because you'd imagine early in the cool season, there's maybe less likelihood of those Colorado lows to be associated with snow or freezing rain. It might just be all rain in all quadrants. if you end up with similar sort of error profiles or not. I think that'd be really interesting to see how that varies. But unfortunately, we didn't consider too much of those differences.
Ian, I'm curious, the one where you have the 4 sort of spaghetti plots with the frequencies of the storm tracks
Yeah.
early on, and you've got those, so now like the white, basically shading the average track pressure. So
Yeah.
those West Canada ones are interesting to me, where like it seems really straightforward on the others, where it's like, all right, it starts out with a high pressure and it develops to low pressure in time. The West Canada ones seem a little less straightforward in terms of, you can still see that they're dropping pressure, but it's less clear. Just curious about
Yeah.
that observation.
Yeah, I think here you're just dealing with a situation where these cyclones just have a lower potential for their development. These are cyclones that are developing with a relatively cold air mass to the north and still a colder air mass to the south typically. So in terms of maybe some diabatic contribution to sort of enhance these cyclones and further the development, you're definitely limited compared to your East Coast or your Central US ones, which sort of have the Gulf of Mexico and the Gulf Stream sort of open for business there. So I think that's probably a big factor there.
Same story with the zonal axis
Yeah.
on too, maybe?
Yeah, and I think that the sort of the zonal axis here more be a function too of just, these tend to be lower amplitude type patterns when we look at the geopotential heights that are sort of just moving along, or sort of weak vorticity maxima associated with the polar jet stream in those locations.
Cool. Thanks.
More
Any other
students,
questions?
or-
I think there's no more student questions, at least not immediately. Melissa?
Hi, interesting talk. So I'm wondering, like, presumably we want to fix this and
Yeah.
have better forecasts. Like,
Yeah.
what is your research pointing towards as the path towards fixing these issues?
I think sort of there's a couple of spots that I think I would zero in on as places to investigate further. I think one of them is to understand how some of the microphysical processes that are being represented within the models for these different events, and if you are indeed getting those situations where maybe you're, let's say, dealing with over evaporation or over sort of exchanges of latent heating than you might expect within those scenarios. I think that could be something that gets dug into. But I think also taking a little bit more of a cyclone specific, let's say, focus on or cyclone life cycle perspective on these forecast errors. Let's say, you identify sort of the errors associated with the cyclones at their genesis time. How do those progress as the cyclone matures? I think that really helps to pinpoint whether in these scenarios are the cyclones really, let's say, developing too fast within the model, within that framework. If you're able to track the errors within some, let's say, normalized approach as the cyclone is moving through a particular region, you're basically then comparing errors at the same life point within the cyclone's timescale, whereas right now we're dealing with cyclones, say, for a bunch of these that might either be just developing as they move through the region, or they might be sort of in their mature phase. So there's a bit of mixing there in terms of where cyclones are in their life cycle as they pass through the domain. Here we're taking sort of more of a perspective of what's happening right near the ground, but I think understanding from a dynamical perspective how the forecasts, let's say, are evolving, or the cyclones are evolving within the model compared to reality might sort of shed more light on some of those processes themselves that might be targeted for improvement.
But your hypothesis would be that the relevant processes are microphysical processes.
I think especially for some of the errors we were seeing with the precip type, that would be my main thought process there, yeah.
Myra?
Yeah, another question related to modeling. You have in one of your slides your temperature anomaly profiles that are related to each type of storm.
Yeah.
And you pointed to the bias higher up, and I believe it's a cold bias between 200 and 300 hectopascals. Yeah, I mean,
Yeah.
that this plot will, I saw that in several locations. So what would you think that is? Is that, I mean, it's very suspicious that that's also where you have your jet.
Yeah.
So I wonder if the model's not really grasping the differences of temperatures in the boundaries of what they call correctly.
Yeah, I think that's a really good observation. We didn't dig into that specifically here too, but I would totally agree with your hypothesis. If you're not, let's say, or in this situation, if you're dealing with maybe that sounding being taken right on the edge of that tropopause break between the equatorward and polar side of the jet, you're going to end up with probably some pretty substantial temperature errors just with some small differences in the position of that boundary. I think that would be a really great spot to pinpoint or look first in terms of what might be responsible for those errors. If you're, let's say, if let's say that jet is too, like one of the arguments we're seeing is that the cyclones are too left of track, which suggests that the baroclinicity is farther left of track, which means these profiles might be ascending through a greater depth of the troposphere than they are in reality, which I think would translate to maybe some of these colder temperatures. So that's a really good hypothesis.
Yeah, that was sort of one of the questions I had in mind was, is there a physical connection between the left of track, slower and more intense? I think there is, but I haven't been able to figure it out in 30 minutes. I imagine you've been able to figure it out over a longer period of time.
Yeah, I think part of it is definitely with the too slow, but also too strong and left of track. If those, one thought is if the cyclones are developing too quickly and undergoing the occlusion process, that's a mechanism where the cyclone pressure is too deep. It's maybe left of its track because it's starting to maybe recurve a little bit forward through that occlusion process. And so that might be part of that sort of
That's
aspect.
one way to connect them, yeah. That's
Yeah,
a good way to
is
think about
if you are not, if the life cycle in the storms themselves is progressing too quickly.
Mm.
Yeah.
Yeah, that's really interesting.
It might be also interesting too, we didn't do this either, but understanding how some of these track errors or what these track errors look like for the different quadrants. So what does a too fast and left of track cyclone look like in the forecast relative to reality?
Yeah.
That might provide even more insight
Yeah.
to dig into.
Yeah, because you might be right about life cycle stage.
Yeah.
And that's just a really, in a weedy aspect of life cycle stage, if it's occluded or not.
Yeah.
And if it ends up in reality becoming occluded, it just takes longer to get there.
Yeah.
And then you also, I think they begin at upper levels, so if you're a little colder than you should be at upper levels, then you're getting a slow start on that process.
Yeah, that's true.
So all that stuff might go together.
Yeah.
That's interesting. Is there any other question? I have one more. Andrea?
Well, I had a question thinking about your Canadian tracks.
Yeah.
And if there's a lot of those tracks in that cluster, when you were showing all the tracks in the clusters, that are really far north. So I'm wondering if some of those events and the ones that are associated with precipitation are more of like a confluence zone than actually being associated with the cyclone itself.
Yeah, I think you're exactly right. Like, especially for some of these storms that are recurving up in towards the Labrador Sea, it's probably some trailing cold front there for sure in that particular scenario too. I think that's where, more partitioning of the life cycle might be really useful. Because here all we require is that cyclone pass through that sort of black box domain here and be associated with some measurable precip at that time. So some of those cyclone tracks are well past the time we're considering. It's still showing the full life cycle, but it's likely some of these northernmost dots here that have maybe some sort of trailing baroclinicity with it.
I'll talk to you at some point.
Any other questions for Andrew? All right, well, if not, let's thank him again for a stimulating